Okay, it's a great pleasure to introduce Ralf Kaufmann from Purdue University. Ralf's title is Noncommutative Geometry in Hochschild Complexes. Ralf, please.
All right, thank you for inviting me, and I hope I neither bore you nor you were disappointed that the geometry is not that non-commutative. So it's maybe a commutative geometry associated to non-commutative algebras. All right, that's why I think the title actually works. All right, so this is the outline. I think I didn't know who was coming, and if people, I expect that most people know this, but I'll do a little a quick review of Hochschild chains and cochains and their structure, and some generalizations of the Linnaeus conjecture and the Linnaeus conjecture itself. And then I'll introduce a package of operations, which is actually from 2006. And but that has sort of a new life in it because you know, we could show that actually not only do we have operations on cochains, but on chains, and there people cared about the Goreski-Hingston coproduct, and that was actually already part of this package. Then it's easily adjustable to other situations, so one can include animation in the sense of Nest and Sigan. And then there's some newer results which I would like to talk about with that I have with Zhengfeng Wang and Manuel Rivera on actions on Hochschild chains and the Tate-Hochschild complex. All right, so just to fix notation and see what's going on. So if I have associative algebra, I have a unital associative algebra at the moment and a module, bimodule, then I can write down the Hochschild chains. They're just M tensored with A tensor N. I put M in the first slot here. This will be important later on. Then because this is an algebra, I have multiplication maps. So I get some simplicial differentials where if I have tensors in A, I can multiply them. And because M is a bimodule, I actually have two maps, one multiplying from the left with A1 and one, from the right with A1, and one sliding this AN around, oh, this should be AN minus 1, sliding the AN around and then multiplying from the left with AN. It should be, it's actually, okay, so cancel. So this should be N minus 1, sorry about that. Okay, so now cochains are, in this case, we can write them down as homomorphisms from A tensor N to M. And again, I have differentials coming from multiplying the arguments and multiplying, because this the function lands in this bimodule, I can again multiply from the left and the right by A1 and AN, and I get these differentials, and then taking the alternating sum in both cases, I get either Hochschild homology or Hochschild cohomology. All right, so now what can you do? So now I changed my module to, actually I could have taken any algebra, but let it be the algebra itself, because that's how I'll go on. And it's actually interesting to keep track of what structures need what assumptions. I will at one point, you know, I'll just keep with AA and then not talk about the AA bimodule M, what you could actually think, you know, what is necessary to go through the steps, but maybe I'll mention it a little bit. So here I have A, so I can multiply functions because they're functions into an algebra. Then because they're functions, I have insertion operations, which means that I checked these 3 times. I prepared them new and I checked 3 times for typos, but then of course you never see them. So this should be, of course, a subscript. So this is, and this should be not 2, this should be tensor. So what you can do is you can take the function, and in the first slots you fill it with the elements you have, and then in the I slot you put your function, which then is of, it takes these elements, and this should be I don't know what that is. And then the next one, so the bracket should close, and then you take the next element and fill it up with the rest of the elements you had before. And then Gerstenhaber realized something nice, namely you can sum over all these operations and you get a structure that is not quite associative, but it's pre-Lie. And what this pre-Lie means is that if I take the commutator, then I get something which is Lie algebra, except that you have to be a little bit careful, and this is true for the whole story, you have to be a little bit careful with signs. So this is not quite a Lie bracket, it's an odd Lie bracket because the operation here, and that's indicated by having it as bullet, has degree 1. But in principle, so what you can do is you can shift the degrees by 1, and then this will be a Lie algebra. And it also, there is a nice compatibility, which is Poisson style, but you have to get the right signs again. All right, so then Gerstenhaber proved a theorem, which is nice, namely, of course, this cup product is not commutative if A is not commutative, because it just lands in A, so why should it be? But interestingly enough, on a Hochschild cohomology, this cup product is commutative. And the way he proved that is to give an explicit homotropy between the two iterations, cup and cup opposite. And that homotropy is given exactly by this circle operation. So the boundary of the circle operation is given, the cup product minus the cup product opposite. And now this Gerstenhaber bracket, so that obviously then is not closed because it's a homotropy. And this is a nice, I'll mention this here too. So this is a nice thing too. There are two things you could look at. And I always have these conversations, actually also with Manuel, namely, if you just want operations on the cohomology or homology level, of course you want closed things. But then sometimes you want actually non-closed things because they should be homotropies. So this is the prime example of something where you have both things happening. Namely, you have the pre-Lie product as a homotropy and the bracket as an operation on the cohomology. Right? So that something is not closed is maybe not so bad. So and then I learned this from Boris Sigan that I should look for this. So he turns it around and says that's actually the more interesting case. Well, he's here, so if he disagrees, he can protest. All right, so now I don't know if everybody knows about operads, and that in a sense you don't have to, but if we go back to this page, then we have these operations, composition I or circle I operations, and I use them to build this pre-Lie bracket, but they stand as individual things themselves and have some standard relations, which if you've actually never seen an operad, it's the best thing just to go home and invent one right now by yourself. You just write down the properties of what these circle I operations have, you do one after the other, and then you figure out that, okay, if you just had a function, you're done, and they're associative in a certain sense. And maybe your function, there was something, and we'll get to that, you could permute these tensors. So that's the other part. If you are allowed to permute tensors, then these circle I's have some equivariance with respect to some Sn action. So, but whatever an operad is, it's some sequence of spaces which has an index n. And a typical thing is Hom v tensor n to v. That's exactly what I used, functions from A to n, or from A to A in that case. And what is an algebra over an operad? So you now take some abstract operad. So this should be O of n. I don't know, it must have been, I have no idea why I have so many mistakes. So I cancel them. So this should be O n. And so that goes from Hom v tensor n to v. And now why is that important? So we have these two operads here, right? One was the, so now this thing is not working. So. All right, so now it works again. So we have these homomorphism, these functions f, and we have two operations, namely, sorry for going back and forth. We have these two operations, and this should not be cap, that should be cup. So we have the two operations, cup and circ. And so these two operations, I can look at what I can generate by these operations on homology. I just have a cup and the Gerstenhaber structure. And the operad which governs these operations is called little e2. It's also called the Gerstenhaber operad. And now something happens. This little e2 is actually the homology of an operad, which is the little disks or the little 2 cubes operad. Again, I'm not going to define that, but what that says is, say I have this kind of substitution structure called operad. If this lives in topological spaces, I could take the homology, and then the homology, because it's a functor, that will also have this structure where I can plug in things into things. And so here there's something which is saying, oh, this operation E2 here on homology or cohomology is a shadow of some operation which lives on topological spaces. And now you can ask about, what about these circle I's and the cup product? They're actually, the cup product actually exists on the chain level and on the homology level, and these circle I's, they just live on the chain level. So you can ask, is there a chain level version which acts on the chain? So this is Delini's conjecture question, which he wrote in a letter to several people, among them Jim Staushev. And the question was, is there an operatic chain model C star of D2 for these little disks with operations induced by the operad structure on D2, which acts on the Hochschild cochains inducing the operatic Gerstenhaber structure on the Hochschild cohomology. And then the short answer is yes. That's a, but yeah, there are some things which you have to say. So the first thing is you need to be careful with the signs. So it's not, what I said is a little too naive. And I don't want to talk about this today, but it, you know, it took 3 months of my life to understand how that actually works. So anybody that has worked with that knows the curse of signs. And the statement has several parts. So there is a chain lift that provides the operation. And not only do we have the operations as linear maps, but you have them as linear maps that fit together in operatic fashion. And then you still have to show that this chain model is a chain model for the little disk. So it doesn't have help if you just have an operatic chain model acting. And then the last thing is, now not only do you have to have a chain model, that's a chain model of the disk which acts operatically, you have to show that that is induced from the operad action above. And so this is a lot to ask for, but it's an interesting thing because it gives you the following interrelations. And this is also what I want to generalize. But this is why, I mean, this has been like in the past, and there's been solutions around for about 20 years. So why is this interesting? So there are several levels where there are interactions. So the one that I already told you about is you have spaces in geometry, then you have the chain level and the cohomology level, and they all talk to each other. Then if you have algebraic structures on the cohomology, you sort of have weak algebraic structures, VG structures on the chain level. So that's exactly these things up to homotropy. So here actually the weak structure for commutative is just associative in this sense. Then the other one I was just talking about is we have these linear operations. They just by themselves, one operation at a time, just like the cup product or a bracket. Then they can fit together in an operatic fashion. And they can come from a geometric interpretation. So there's some geometry in the background which makes these things actually work. And then you can ask, well, what about the differential? So these are just linear operations. I could write them down. You always have to prove compatibility with the differentials, or at least you would like to. And then, you know, does that DG extend to the operatic level? And is that DG operatic level induced from the geometric level in the sense that you took a chain model? So you had something in the geometry, and then you took a chain model, and this is a choice. You have to pick the right chain model. It's not clear because the chain model is very flabby. So you have to get this on point. And then sometimes you want to reconstruct. You start here, then you have a weak thing, and you ask yourself, is there a geometry? So this is somehow where I said, you know, what the geometry of operations. And what happens then is that sometimes it's easy to lift the linear part, and then you get the DG part on the chain. And that tells you how to actually compactify your spaces. So there's sort of a reverse operation, which tells you if you wanted to have DG, your spaces have to satisfy certain equations. Here's a short rundown of the history, which is probably, I forgot something because there's so much going on, but I think I did pretty well. So the first proof or non-proof was given by Getzer and Jones. So there are many parts and things where things can go wrong. That's why I spent some time with that. But every time something goes wrong, it's an opportunity for you to find more structure, and that's more or less the story. So they had a cell model which was not operatic. They used Fox-Neuvert cells, and that doesn't work cellular as an operator. So that's the operatic part was off. Tamarkin and Kontsevich solved it. Well, again, this is a story. There's like Tamarkin had some proof. Kontsevich improved that so that it's true. So I think that proof is true. Voronov gave something which works over Q. Then Kontsevich and Sollmann did a very nice proof in '99. They generalized to A infinity and introduced a very nice combinatorial gadget, this minimal operand. So this is the optimal thing that you have working on the chain level. Kent doesn't get better than that. It's a graphical thing, which is in terms of trees, and that's what was sort of why the story still went on is because it wasn't so clear how the geometric part actually works. Then McClure and Smith looked at this simplicity, but they have the wrong recognition principle. So in a sense, they didn't prove it. But they introduced a nice operand, this surjection operand, which is in a sense just a variation of this minimal operand. But this is more easily understood by people that are simplicity minded. But it's the same as this minimal operand. And so they also, then they had a second proof because I think they realized that their proof wasn't correct, which is also very influential, but also there they didn't prove that things are operatic, but they introduced something good again, which is this a numenoidal product, and I will use that and new operations, which because this is a box times product, instead of a cup, it becomes a square cup, and it becomes a square cup I, and these are not really the correct operations. That's the joke. They're off by a degeneracy map, and that's why they didn't really prove that it's operatic. But it's very important to have these. And then at one point, I gave a new proof because I was interested in the little this operand, and I found a new model for this using spineless cacti. Cacti were invented by Voronov. And this is really nice. So it realizes this combinatorial structure here of Kontsevich and Sollmann as a topological space very easily just polysimplicity. So you have a cell complex, and that cell complex has cells which are just products of simplicities. And so and then you can prove that that is a model of FD2, so that works. Now, more operations. So what else can you do? So I thank Masoud for pointing this out. I didn't know. So in '99, Masoud already looked at operations on cyclic chains. And Meniki in 2003 found a BV operation on cohomology. And actually, so for this, you need to assume that your algebra is Frobenius. I'll go through that in a second as well. And so then in 2004, I gave proof what I call cyclic Dedini conjecture, but that I should have called it a Tamarkin-Tsigan conjecture. And again, I'm sorry for that. I just didn't know. So they conjectured this in 2002. In 2000. And then Trada and Zenarian gave combinatorial operations and algebraic string operations for open close. But again, there's not much in the operatic sense there. Then in 2006, I gave a package of operatic actions, and I'll use these. And this actually fixes the McClure-Smith proof, the second proof. So although the proofs had little gaps, I mean, they got filled by the work that I did. And then we could do the A infinity in polytopes. So that realizes this M of Kontsevich-Sollmann in terms of polytopes. And you can do the open closed. Then you can do the cyclic. So Ward did that in 2011. And then we turned the page. Wald and Westerland gave some other open part and basically the same closed part as we had, but did it in A infinity. And now this list is the one that I want to get into. So Zhengfeng Wang realized operations on Tate-Hochschild complex just recently in 2016 using cacti. And then Rivera Wang generalized these things. We're currently working on a paper together. And I learned from Boris Tsigan that he and Richard Nest have a book forthcoming, and he shared some of that. And I learned about animation, which fits into this framework as well. So more of that longish story is it started a long time ago. There are all these operations. They fit into nice things, and they fit into stuff we still care about. All right, so what's this package of information? Here's some notation. If you have a Frobenius algebra, you have a non-degenerate symmetric pairing. You have a co-unit or a co-augmentation, whatever you want to call it, epsilon of A taking the bracket with a unit. I like to call this an integral. It's like a trace. This is cyclically invariant. So this is epsilon of the product here. So it is a trace. Then you have a co-product, which is the dual of the product. Then if you take the co-product of one, I call that the Casimir element, like all physicists. Wait, I have some physics background, so I have an excuse. And this is just Sweeter notation. And if you take mu delta of one, you get this class, this element in which I call the Euler class. So that is because if your cohomology, if your A is the cohomology of a compact manifold, that is the Euler class. All right, and then how do these operations work? There is a strange coincidence if you have a Frobenius algebra, because I can take my Hochschild cochains and I'll use check as a dual because otherwise I have too many stars going on. And you see that if I dualize, I can either dualize everything into A check tensor n plus 1 or A tensor n plus 1. And CH lower n of A was A tensor n plus 1 to start out with. So if I forget about the differentials for the moment, linearly, this is just the reduced tensor algebra, which is A tensor TA. And so magically, these two things become the same. And then something nice happens, because if I just look at T bar A, I can just take tensor products of this standard product of A. And then I get some non-degenerate bilinear form there. And actually, everything works out nicely. If I remember which side is which, the differentials work out and they're dual to each other. So it's actually not so bad to identify both these things with the reduced tensor algebra. All right, so then we all know the standard coproduct, although we have to be a little bit careful. We're working with AA bimodules, but I'm just tensoring over the ground field. And then this should be tensor. It's because of I know what the problem is. My macros are OT and TO. So this is times TA. And so it's just the standard deconcatenation product. And now what's interesting is for these operations, there is another tensor product which you could use for A modules, A bimodules. You can just put an A in the middle. Now that sounds a little strange, but there is a nice deconcatenation product which goes from A to TA tensor TA. And I call that lozenge or diamond. And what it does is it goes up to AI minus 1. On the right-hand side, it starts with AI plus 1. It starts with AI plus 1. And here there is AI. So this is exactly the type of operation we had when we looked at the substitution circle I, because we plugged something into the I's place. We had a left part, a right part, and a place where we plugged in. So that's exactly this, mimics this. Then how do I get from one to the other? So I can, I have units and co-units. So I can just by using the standard unit constraint, I can put a K into here and then go with my unit from K to A. So that gets me from M tensor N to M box times N. And then I will use this notation total eta, where I'll always have this factor of A, which I'll call the modular variable. So I'll leave that alone, but all the other box times, I'll insert a 1. And then the inverse operation is given by reading out the factor of A by using the co-augmentation method. All right, so then, so how do these operations work? The first thing is to notice that the reduced tensor algebra is K box times A, which is just A tensor A. And then, as I said, I want to leave the first leading A part alone. And so I'll just write this iteration of this lozenge product, leaving this part alone. So it just acts on this guy. And so what do I get? So I get alternating words, algebra, word, algebra, word, algebra, word, and the word is always in the reduced tensor algebra. And I'll call these T bar A's blocks and the factors of A intricacies. So I don't know if there's somebody actually foliation minded, but there is a nice way, and this is actually how I came to work with foliations. And this is an algebraization of foliations, and these are really the instances of the foliation. So that's what I did with Bob Penner. So this is so then you can ask, what can I do with these things? So I have this lozenge product, I have permutations, I have my pairing, and I have the integral. And it turns out there's just some set of universal operations you can write down, which is, so first prepare your tensors by pulling them apart, but making these instances. Then taking a block permutation where you only permute either the factors of t bar a or the factors of a. Then you pair together factors of t bar a, and that's part of the data. This is this I that tells you which factor of t bar a I'm supposed to contract with which factor of t bar a. And then there's this integral. So there's some factors of a, and I apply this the co-unit, the co-augmentation map to some products. And what is tricky is how these products are chopped up. So, and then what is the data given here? So it's this n1 to nn. This is the powers of this lozenge, this involution, which tells me where I should put these things. And then actually that data gives me where I should use my integrals. And the fact is that actually what I'm looking at is a ribbon graph. So I can define a graph that will have n vertices. So the n comes from the fact that I have an n here. So I have n vertices. There will be ni half edges. So to each vertex, I'll start. So it will look like this. I'll have ni half edges. And then I have my pairing. So if I have a half edge here and a half edge here, I will pair them with this pairing I. And so that will give me a graph. And now I have more data because this ni, remember that was a word, and that word started with a and then word and then a and then word. So this actually, so these words come in a cyclic order. They actually come in a linear order, right? So secretly this was, this was the W1, W2, W3. So they come in a linear order. So of course, then if I have a linear order, I have a cyclic order. So I have a cyclic order. So that already makes the thing into a ribbon graph. I call the things in between here angles. So this is where the AI would go. So this would be A0 would sit in here, the WN would sit here, right? But I'm just extracting the combinatorial thing. I'm not decorating at the moment. And then so then the linear order tells me that this A0 is the first one. So this is like the first angle. And I'll call that the module angle because that's where this leading coefficient always sits. And so actually I did the illustration. So if I had, I'll use this. So let's say I have a very simple thing. I just have 2 in each one. And then so this would be 2 things. I would have a linear order, say, and then say A0 and then W1, A1, W2. And then I would pair this. This would be the pairing like this. This would give me the I, and I would just see a triangle. So this is a nice example. I'll work with that example in a second. All right. So each ribbon graph has cycles given by the involution followed by the successor. So for my triangle, this is actually fairly easy. So here I can go on the inside. I would have one cycle, and on the outside, I have another cycle going that way. Sorry, this one goes that way. Sorry, no, actually they go the other way around. If I use the orientation of the plane, so I have 2 cycles and the outside goes counterclockwise and the inside goes clockwise. Clockwise, I said. So it's like we teach our kids in Calculus 3. So this is a disk and you have this boundary going inside and outside. All right. And then, so because the angles are marked by these elements AI, right? I mean, I have an A0 sitting here, and I would have maybe a B0 sitting here. There's a B0 and A0, A1 here, and maybe there's a C1 here if B1 is here and C0 is here. So I can go around this angle. I'll see some elements of A, and that's the one that I integrate. So here I'll integrate A1. B1, C0. All right, so that is an operation. And I would say you can't argue with the definition. but where in the world did this come from? So this came from some geometric thing, namely so the theorem I proved back in 06, appeared in 08, is that these linear operations define operatic correlation functions. So that means you can stick them together using a Casimir element for open cells of the moduli space MGN. So if I have a ribbon graph, it's sort of well known from hyperbolic geometry or Schrebel differentials that these have something to do with actual surfaces. And they have something to do with foliations. So it is really true that that ribbon graph I just constructed has something to do with the surface. And this is where all this thing comes from. So the fact that these things work, we knew ahead of time with Bob Penner because we were looking at the surface geometry. And that's how these things end up working with the ribbon graphs. And you have to be a little bit careful with open moduli space. And this comes to this that you have to maybe look at compactifications, because notoriously it's not compactified, so it's not really a CW complex, but it's an open subset of a CW complex. Yes, Theo.
Yeah, can I interrupt? Sorry.
Yes.
So yeah, indeed, the stuff you mentioned also appears in perturbative expansions of matrix integrals.
Yes, exactly. That's where it comes from. Yes.
Over ribbon graphs and stuff like that. So I'm just wondering if there is a way to formulate these things in terms of matrix integrals and then perturbative expansions, so that all these operations have some manifestation there, so to speak. I mean,
I'm tempted. I'll take your question in the question session.
Okay, yeah.
Otherwise, I'll talk for 15 minutes and not.
That's right. Yeah.
That's a really, really good observation. Yeah. All right. So then you can actually do modular operands and extend it to open close, but there's something nice. So it's like, how do I construct the surface? And I'll get to one of your points. So how do I get the surface with arcs? So for every vertex, for every cycle, I'll take a 2L-gon if the cycle has length L. Then I'll glue together these 2L-gons according to the orbits of the involution. And what you get out is a surface made up out of boundaries, where there will be n boundaries, which were your original vertices. And the gluing things where you glue it will be arcs running from boundary to boundary. And there'll be sectors according to this. So these are the angles. And there's exactly one sector in each boundary, which is marked by the module variable. So here's a picture. So here's the triangle again. So it's better if I had it prepared. So for each, so I have 2 cycles, cycle 1, cycle 2. They have 3 sides and 3 angles. So I gotta take a hexagon, and I have these 2 hexagons. Then I glue them together. So I should, this is a vertex 1, 2, 3. And that is 1, 2, 3, and these sides are the sides here, which are part of the cycles. I glue them along the cycles, and I see actually this picture here, which is a surface with arcs. And then it's kind of nice that I can look at the ribbon graph that's dual to the surface, and this actually goes exactly to this Schrebel picture, what you were saying. So this is the standard ribbon graph that you would see. So this is not the standard ribbon graph. The dual graph is the standard ribbon graph. Okay. But then, so this is also where the matrix integrals come in. So if I wanted to have a DG thing, then if you look at the differentials, so I had these linear things. I said the next level is look at the differentials. I know what the differentials are. They're the ones from the Hochschild complex. So you immediately can compute, it's a computation that if something is supposed to be compatible with the differentials, I will have to go to a compactification. And that compactification is the Penner-Kontsevich compactification, which they independently figured out actually how to do matrix integrals. That's exactly what Kontsevich used them for. And so then if you go to the compactification, there is a little modification, eta, so that's eta is actually the form. So I have this thing, but here, instead of just taking the integral, what I should do is I should take the value of the open TFT associated to the Frobenius algebra A. So I had a much more complicated formula in 08, and this is the easiest way to say it. So I put this into a paper which just got accepted to JNCG, which I just mentioned. So it's a paper of 18. So there's this nice universal formula which tells you that now if you have this cell in the compactified moduli space that corresponds to some sort of graph with extra decorations, for that you have an operation. And that works DG. Now you can ask for even more. Is there like a prop action or something like this going on? And then this is where the link comes to Sullivan diagrams and to string topology. So now now it's kind of, so it goes two ways. First, you do algebra. You say, well, okay, so maybe I want to have a prop, so multiple inputs, multiple outputs. Remember what I just had there was, many inputs going to k, just a trace. Very complicated sort of trace. And then, if I want inputs and outputs, I know how to do that. I just take, some of these things here and just dualize them. But I have to say how many and which ones. So that's part of additional information, a partition n plus m of some large n. And then I keep the first n factors on the left and put the m factors on the right. And now I have input and output. This is not very deep yet, but that tells me that to an operation of a cell, which is given by this graph, I also have now a prop operation on Hochschild cochains. And so what are these Sullivan spaces? They answer the question, and this is an insight of Sullivan, which is, I don't think he thought about it this way, but it works out that he defines some asymmetric structure. It's very important. It's an asymmetric structure. It's a partial compactification of the space, a bordification of the space, such that this is a DG prop. So that's the theorem. So what you have to do now, so you have to single out some ribbon graphs, which I'll call Sullivan type. And that means that for these arc graphs, they only run from inputs to outputs, and all inputs are hit. So there's always an arc coming from input. You may have empty outputs. This is part of the compactification. You're allowed to do compactification in a sense on the outputs, not on the inputs. And if you do that, you can retract to the CW complex. And then with this decoration, you can write a correlation function again, or an operation again, where now I use this eta out tot, which I had before. So that was in every slot, which is not the module slot, insert one. That's asymmetric. I only do this on the outputs. It's very important. And then magically, this becomes DG prop. That's not that easy to prove, but it does. But the important thing is there was this asymmetry here where I put one in the output angles, which are not the module angle. All right, so then the theorem says that Sullivan space is a weak prop structure, so it's only associative up to homotopy, and has a chain model in the CW complex, which is an actual DG prop, and that DG prop acts as on the chain level as a DG prop action on the Hochschild complex. So again, that's the full Monty. It's like you have the space, you have the differential, you have the chain model, and all the operatic structures are induced, propic structures, except that you have to be a little bit weak here. So this has to be weak. So you have to go to the homotopy category there. So it's a homotopy prop. So that's nice. And so what does it look like? So here's some illustrations. So here this just means, so this is this word part. So this has length 3. Maybe there's A0, A1, A2, A3. And then I contract along here. So this is this word contraction here. That's a word contraction. And this is the module variables with here. And here is an output angle. So input, input, output. And I can either say, I just want to have a 1 here, which is contra, well, it makes sense, but it's now marked by 0, or I just put any other variable here and I mark it by 1. And I can do the same thing for this kind of picture and either mark the outputs by 0 or by 1. And what do I get? This one actually will give me the cup product. This will give me a strange cup product, the square cup product. This will give me the circle I operations. And this one will give me the square circle, the square I operations, which look like this. So I take 2 functions, and now I take even more variables, and I leave the first alone, the last alone. But here I take the function and I use the A bimodule structure on the left and right. So I have 2 more elements, 1 here, 1 here. If I make them 1, it's exactly the circle I products I had before. So that's how this works. And that's in a sense where this McClure-Smith proof isn't complete, because they use these operations and show that they're operatic, but they don't induce the correct operations. You should use these degeneracy maps. And then you have to show that the degeneracy maps commute with composition. It's just something you have to show. And again, it's not completely forward. And then you can see that you get something like cons operator B or N actually, and animation. So here's the picture just of this arc arc graph and that there's a DG. So the DG, I didn't mention that, it just deletes arcs. So if I delete one or the other, I get just the graph as this one, which is the same. And in principle, so if I do all these words, so if I arrange the words correctly, what I do is I slide around the words, and this is the formula. And then, as I said, I learned from Boris Tsigan, what I could do is, well, if I slide this around, of course, I can insert into this pairing, I can just insert a function. Probably I want that to be self-dual. But okay, so if it's Frobenius, if it's not Frobenius, I can just insert it. But if this is self-dual, I can just, that will, you know, apply the function to this f. If it's the identity, you just get the original con B operator if you take the epsilon here, which means that you label this one by 0. And if you label this one by 1, then you actually just get the operator n, which turns around your tensor. So it's kind of
Ralf, sorry, what is an animation technically? I mean, is it an
technically, as I say, the book is being written up, but as far as I understand, an animation is exactly this type of thing that you have. But you can invite Boris; he can tell you about this. So is that you also have a bunch of functions which give you morphisms or modular operations that you can also invoke in your set of standard operations.
Okay.
And again, I learned this from Boris, so I'm repeating his stuff, so I feel a little silly. So what he's saying is, if you just look at cons operator B, that had the boundary is 0, so that actually is an operation. But if you do this animation, then it sort of matters if you do the operation on the left or the right. So this is sort of the, sorry, you have the identity or you have the operation. I messed it up. And then you see that this animation is a homotropy from the identity to identity tensor F.
I see. Okay.
And so then sort of in a sense, either you say you destroyed the fact that B was a cohomology operation, or you say you upgraded the fact that the deficiency that the boundary was 0 to making it a homotropy.
Okay. It's kind of thing maybe, yeah.
Right. So it's like a coloring, right? It's a coloring by functions. That's how I think of it.
Okay, thank you. Yeah.
All right. And now I could have done, I said this in out, so I had this kind of duality. So when I showed you the product, I said in out, right? I mean, here I said in out, but I could have said the opposite. I could have said out in, and that's a kind of input output duality. So now you can ask what happens, and then there's something intelligent that happens. Actually, that cell, instead of becoming dimension 0, becomes dimension 1. It has 2 boundary components. You see, this is actually degenerate on the out, so that's allowed. So this actually has the full asymmetry that is present in the Sullivan prop. So I can take my in and out, flip it, and then these ones I can't flip, because if I flip it there, I would have an empty in, which is not allowed. But then you can actually just compute what this is. And here is this where you would see the action of this open TFT. Namely, in principle, what you get is you get these Casimir elements, and you have to conjugate by the Casimir elements. So if you go around now, you'd see B0, C1, C0, C2, and then A0. So you have the integral over that. So you get something like the Euler class. If it's commutative, you get the Euler class. Right, so and then you can do this computations, and out comes a nice operation, namely unnoted cochains. You can write out the operation. It's just the one I read off. You go through the motions. So if you want to see the details, this is in this Hochschild note on Hochschild operations paper. And these have a boundary. And so they're not co.
Oh, Ralf is muted, I think, yeah.
Am I?
No. You're okay now. We can hear you. Yeah.
All right. My connection is unstable. Hold on. Yeah, maybe I should not.
Only very briefly there was a problem, but no, that's okay.
Okay, so this has this factor of delta of 1 squared. So now something happens which is interesting. Now the type of Frobenius algebra plays a role. If it's geometric, it's nilpotent. And then this is E tensor E, which lives in the highest degree, so it kills almost everything. If the Frobenius algebra is semi-simple, then you can more or less normalize it up to homotropy. And then that factor is just 1. So everything is allowed. So it's kind of interesting. So, but for the topological applications like string topology, you can figure out that this thing factors through the constants. And then, so what Goreski and Hingston used is exactly a sort of a factorization of the homology of the loop space in the Jones model of Hochschild cochains on the cohomology with coefficients in the homology, and then reduce that. But you even have to reduce a little less. You only have to reduce by the constants. So you just have to not only not the constant loops, but you just have to do the constants, not only CH0. All right. So, but that so there's no way one can. I mean, I could spend half an hour just explaining why these formulas work this way. But what I want to say is, I draw a nice picture. That it's not just a nice picture. You can write down the explicit formula for that and compute everything with it. It's a little tedious. For every operation, you can do this and you get an explicit version. All right, so here's more examples. So this is maybe I'll skip this one. So now I want to spend a few minutes on sort of how to generalize this first to chains. And so here I just write yoga 1, yoga 2, and then a mantra. And it's actually kind of easy if you think about it, but you have to come up with the idea. I came up with this idea only because I talked to Zhengfeng Wang, so he sort of helped me see this. So if I have hom VW, that's just W tensor V dual. And then if I dualize everything out of it, that's just hom W dual to V dual. Okay. And this is the way I looked at them anyway. So I gave these functions to K, and then I said, okay, these are Hochschild cochain operations. Now I can do the same thing here. I had this is where I started out, namely reduced tensor algebra. Then I dualized it in this one. That was part 1. But now I know that the dual of the Hochschild chains, cochains are the Hochschild chains. So I could use this form and I get something on the Hochschild chains, but I switched M and N. So then the idea is, but it all comes from this tensor algebra. So then the mantra becomes Hochschild chain inputs are Hochschild cochain outputs, because I can put them on the other side. And Hochschild chain outputs are Hochschild chain cochain inputs. And the difference between inputs and outputs was that I used this eta tot map, right? Where I put the ones. So I put them on the inputs, on the outputs. So for cochains outputs, for chains inputs. It's weird, but it works. And so then you can do both at the same time, so that then you have to designate your boundaries not only as in and out, but as homological or cohomological. That gives you a 2-coloring. And then you can apply the same universal formula for correlation functions, except that you should put ones in the inputs that are homology type and ones in the outputs that are cohomology type. And now you get a 2-colored prop action extending the operations that Rivera and Wang found for this double complex, for this Tate-Hochschild complex. They found very nice operations that are mixed operations. And for instance, just not even looking at the mixed operations, if you take the dual of the coproduct I gave you, you'll get a product in Hochschild chains. And this is the Goretzky-Hingston product. And again, you can just go, because this is explicit, right? I mean, it's just an explicit formula. You can do the dualization. You can figure out what it is, and this is what it is. So there's an explicit formula there. So and then something nice happened. So this was unexpected. So Rivera and Wang, they found nice triple products which take 2 cochains and 1 chain, or 2 chains and 1 cochain. And this is something more general, like a cap product, where you would take a cochain and a chain. Right, you get a cap product, so things among themselves gives you cap products, chains and cochains give you cap products, and then they have this triple product. And it's very important for them. So we looked at what the triple product is, and it's a very nice arc surface. So if I dualize this back to just an operation on so maybe I should write this. So the operations are of the type that you have CH star tensor CH star tensor CH star to CH star. So then if you dualize or vice, other way around, but if you dualize this thing, you get this. And this is a nice operation. It's a 2-2 operation. It's a 2-2 operation. Oh, this is tensor. It's a 2-2 operation. And that 2-2 operation, you can ask if that is actually a double Poisson bracket, as Vandenberg put them forth. And it's true. And you can prove the Leibniz property. So it's actually kind of astonishing. So that is really nice thing. And this is actually, it is a homotropy, but I don't have time to say that. So it is a homotropy for something. So we figured out what homotropy that is. And it's, we didn't know about this work of Judo Kontsevich-Vassopoulos, but it's very related. So you have an A-infinity algebra with only a mu3, mu4, or so you have mu3, but mu4 and higher is 0, mu5. And then they construct this, this double Poisson bracket. And so this is very similar to what we did, except that, you know, we just did it independently. And we have a series of higher brackets, but we only have a series of higher even brackets. This has something to do with going into out. There's some weird symmetry going on. Still thinking about what the out brackets are. All right, so then here's a nice theorem that's in this forthcoming work. So we can make things work also on this Tate-Hochschild complex. So we have this double colored thing, which works at the same time on homology, cohomology. And now you want to get a single colored thing. Yeah, I'm running over time, but I'll be done in a sec. This is the last slide. So a single colored thing. And then this was the great idea. You know, you take a mapping cone where you have this map gamma of A, which is actually conjugation by the Casimir element. So we've seen this actually in the in this Goreski-Hinkson coproduct. This was this term delta 1. So these appear that this, or when I was reading off this thing for you, I said C1, A, C0, B0, C2. So this is exactly this term. So, and then they showed that then actually you get this mapping cone as a complex. And what we can do is we can show that there's a, we can extend our operations, extend to this thing. And then reversely, you can ask, you know, where did this come from? Is there a space? And it's interesting, that space is something happens because you're making something. So what you're actually doing is you're taking two intervals and gluing them to an S1. So you're actually changing the homotopy type in this space. It's a very interesting space. And it's a cover of the Kontsevich-Penner compactification, where you have to identify stuff. So this is, you know, going backwards. So now you read all the algebraic stuff you ask does come from space. And now the space is sort of the quotient space, which is a cover of this Penner Kontsevich thing. All right, so that's it. Thank you.
Okay. Thanks very much, Ralf. Let's thank Ralf for a beautiful talk. Yeah. Any questions or comments for Ralf? Yeah. Yeah, it looks like I don't see anything in the chats either. I mean, just one other question out of curiosity. Perhaps it won't work, but you know, there are these fantastic Steamrod operations in just cohomology of spaces, and right. they exist exactly because this cup product is not quite commutative. It's only commutative up to homotopy, but it works only if you go to mod 2 cohomology. I mean, somehow, but this has never been tried on the level of algebras or something, even for commutative algebras. I haven't seen anything like that, but it's very much like in the same vein of things you're talking. So I don't know. I mean, it's a very naive question. Yeah.
No, it's not naive in a way. It's like, it's exactly like your other question, and because it's actually, I think it's true. So so we just wrote a paper with Anibal Medina where we looked at these Steamrod operations for cubical things.
Oh,
and we're writing a paper with Clemens Berger on how to realize cubical, the moduli space as cubical complexes. So I sort of pop Penner has them simplicity, but this is actually a simplicial subdivision of a cubical complex. And we know how the Steamrod operations act on the cubical complex. So whatever your question is, those things actually are converging. So we have Steamrod operations on cubical stuff. These spaces are actually cubical cell complexes, and so we can actually see how this works out. And it's an excellent question. Yeah. It's an excellent question.
Okay, well, I'm glad to hear that. But so I mean, there is I mean, you mentioned prop. So as I understand, props are to parameterize things like Hopf structure. So you go like co-products and higher generalizations.
Right.
You mentioned prop. I suppose you know exactly what prop this one is that you have. I mean.
Right. Yeah, I wrote it down. So I'm just drawing stuff. Yeah. So.
Yeah.
So this is, this is a co-product. This is a product. Right, this goes from 1 to 2, or this goes from 2 to 1, and this will go from n to n. So if you have nm, oh, I'm not sharing. Yeah, this is why you're looking. I'm just writing for myself. That's not helpful.
Okay.
Right. This is better.
Yes. Yes.
So what I'm saying is usually these are this operad, right?
Mm-hmm.
And this would be like a co-operad. Right, this is 1 to n, and this is n to 1 operations.
Right.
And then if you have both of those, if you want to have those together, then you need n to m operations.
Mm-hmm. Mm-hmm.
And this is where the props come in.
Okay. So yeah. So
that's just what that says. And then sort of for the surfaces, and this is what Sullivan was thinking about, is like, and what you were saying, like if you take sort of Hopf algebra is actually hard because the Hopf equation is not so easily written, but it has, the easier one is a Frobenius algebra. And so that has like, but it's like anytime you want to have an equation where you first do a product and then a co-product is equal to something, right? Yes. Then you need something like a prop, or in that case, Bruno Wallet would say you need a properad because it's still connected, but that's not quite right either. But but that's where the props come in. But Sullivan was really thinking about just gluing surfaces onto surfaces, so many boundaries onto many boundaries, and that's what he was thinking about.
Yeah, that's what he calls a string topology.
That's the string topology, exactly. So I think I said this very, very fast, but maybe I should say this in the next page. So what I was using when I'm saying string topology is it's just that if you have the loop space of a manifold and pi1 of this n is 1, then there's a nice theorem which tells you that the cohomology of the loop space, the homology of the loop space, this is isomorphic to the Hochschild cohomology of the Hochschild, of the chains on M with co-chains on M. And this is where the string topology. So this is where the algebraic string topology.
I suppose there is also a cyclic version of that, also in terms of equivariance or something.
Right. Then there is an S. Then you could have an S1 action. And that translates here to BV, but then now you need your M to be compact. And then you see that, in a sense that, then you have H star of N is isomorphic to H star of N. I see. And then on the chain level, you have to be careful. Okay. So the expression, and this is where the cyclic stuff happens, right? Yes. Right. This is what I was sort of looking at, this Hochschild co-chains of right. I mean, basically H star of M with coefficients in H star of M. Okay. Right, this has this PE structure that I talked about.
Let's see. Okay. I see there is a question in the chat. So should I read it? You can read it, right?
I think I can read it. Hold on. Except that I have my. Can you please explain a bit of the relation with the work? I'm not an expert on their work, but what they do is they almost write very similar graphs. And now I don't have any extra pages, so let me just do something else. So open this. Notes.
Maybe hard to say, but I think double Poisson brackets, when they appear, I guess it indicates that.
This is Boris.
Yeah. Can you hear me?
Yeah.
Badly. So when you said something like when double Poisson brackets when they appear, and then you missed the punchline.
Yes, it has something to do probably with operations, not just on chains and cochains, but on chains and cochains of tensor algebra or tensor products, tensor square, tensor cube of an algebra, with respect to, itself shifted or twisted by the cyclic shape. So I don't think something like that. And also I would say that you mentioned Steamrod, but again, in positive characteristic like Kaledin, and also better maybe in topological Hochschild homology, there are also those Frobenia. So again, I think it's still far from understood, you know, the correct scope.
Right. So yeah, let me answer two things. I think what they start out is you have maybe a cyclic like an A is a Calabi-Yau algebra or something like this, and an A infinity Calabi-Yau, but you have mu3 is okay, but mu4 is mu5 is 0 and so on, and then they show that this has a double Poisson structure. Double Poisson bracket.
I see.
And basically also by dualizing. And so what we had was this, I took this mu3 from CH star tends to CH star, tends to CH star, to CH star. And then dualize this to CH star, tensor CH star, to CH star, tensor CH star. So, and then this actually, this is this double bracket. And then the funny thing happens is that this is a homotropy. So this is a homotropy. It's a complicated one. So the surface, it looks like this. It's very symmetric. That's wrong. So it's like this. It has in, out. So it works. It's a pair of pants if you want. And then, sorry, it's not a pair of pants. It looks like this if you want. But it's harder to draw this way, right? Maybe in to out, to in, to out, to in, but it's cyclic in its thing. And then it has 4 boundary components, and you can write down these are combinations of delta op and mu. So it's a kind of weird equation, which I haven't seen. I mean, I can send it to you. I can also show it to you because I have the paper here. But it's a homotopy between how mu and delta op actually interact. So maybe that's what works. It's not. It's like at first I thought it's like yet another type of bialgebra, like not bialgebra, but some type of algebra like bialgebra, Hopf, or like a Hopf algebra or Frobenius algebra. So something with delta and mu, and then switch them in some way. But it actually involves mu up and delta up. Mm-hmm. So what happens? Mm-hmm. Yeah, sorry, go ahead.
No, please.
No, what I wanted to say is that actually what happens is there are 4 boundary components, but they add up to 2 things, and then you can see that you basically get 2 terms, and one is with delta up and mu, and the other one is with mu up and delta. Mm-hmm. It's weird though. I don't know. I haven't seen that equation before.
Thank you very much. I don't know if I misunderstood, but I think that you said something like also the even higher multiplications cannot be 0 in some moment, or maybe
right. So what we have is a weird thing. So this is something new. If you look at it, of course, these differentials, I mean, because you have to satisfy these A infinity equations, but they are very simple if half of them are 0, half of the UNs are 0. So, and then we have a sort of nice series of higher brackets, which are exactly sort of just generalized. It's because I can even draw the picture for you. It's the same type of picture. I go in, out, and then, and then this should be, oh, now it doesn't work, right? I go in, and then it should be out. So you see, I have to take an even number of boundary components. Mm-hmm. And then I can write a thing like this, and this will work out. That gives you an n bracket. This has n inputs and n outputs. Mm-hmm. So it satisfies the Leibniz equation, and all these brackets, actually, they fit together in a nice way that you can also write. And we found this way that they fit together, and they fit together in a way which are some equations that Chaz and Sullivan have in their paper in the very back when they're looking at S1 equivariant actions, actually. Mm-hmm. But at the moment, we're still a little puzzled what this means.
Wow, it's impressive. Mm-hmm.
Mm-hmm. So that's, I mean, and you see, I have problems doing the even ones because if I go in, out in a cyclic way, I mean, actually, the best way to think about them is actually as a cycle. And really, it goes in, out, in, out, in, out. Mm-hmm. So that's the best way to. This is one of the graphs actually I had before, like my triangle. My triangle was one of these graphs, except that now it's like a quadrangle.
Mm-hmm. Okay.
and 2 n-gons.
So
yeah, that's a fantastic story, and you can maybe perturb it like we did with Mani and Zaghi. Oh yeah, that was the one thing I want to say. So it's actually kind of interesting. I wonder, because these matrix things. So I don't know what happens with the matrix. So I don't know what the matrix theory should be. The compactifications that Maxim used appear, and they're forced by the genus. If I take a differential, then I can do the Hochschild differential. It just works. It's algebraic. It does not care. But what happens is exactly I get these things from the boundary where these Euler classes appear. You can just do that computation. So you have to move. So we have a way to go to the boundary. But what the matrix thing is, I don't know. On the other hand, it's kind of funny because we looked at these gravitational with Kontsevich, with Manin and Zaghi. And this is like this series. It's very close to this kind of series where you perturb stuff. And that is also related to matrix things. So there might be something. But that's just why, now I'm just widely speculating.
Yeah. I mean, the underlying structures are very similar, yeah. Okay, so looks like there are no other questions or comments. I don't see. Well, let's thank Ralf.
Just for a second. So the slides are available, yeah?
Yes. The slides, yeah.
That you could add or send also something related to this last discussion. Yeah, maybe even this this picture, or you mentioned some equation that you could send.
Yes. Hold on. If you have 1 minute, I might actually find it.
If that's okay, Ralf, we can post the slides if that's okay with you. But,
that's okay, yeah. I don't think I'll send you these scribbles, but the rest you can post. And actually, well, if it's not, I might want to fix the typos. I mean, I'm always bad with typos, and it's really hard for me to find them. So let me try to fix them. I send it maybe after the weekend. Is that soon enough?
Yeah, that's fine. Yeah, fine. Absolutely. Yeah. And maybe Boris also will receive the end parts, which you don't want to post, but that's fine. Yeah.
Right.
Okay.
Okay. No, but I wanted to show you this PDF file. Sorry about that. Hold on. Well, I mean, I'm co-host, so if you want to leave, I think, and Boris wants to stay, then I can. But I just found it. Okay, so. Let me share the screen, stop share, new share. So here's the equation. So that's the picture for this equation. And all right, so the algebraic equation is this one. So that's the homotropy. So you use 4 terms, and it's mu tensor id tensor delta, and then delta op and mu op delta op and mu and delta.
I see. Oh, there is a Swiddler. Oh no, that's a Swiddler.
Yeah, this is in Swedish notation. If you actually want to see what that is, if you don't care about the pi 2 3, so
of course.
If you just want to see what's what it is on the algebra, that's that. And so this is, and that's not that easy to figure out actually. I think if you did. We did this, and I did a pictorial computation, and there was a big and forth between the algebraic computation and the pictorial one to get it quite right. But this is, I don't know if somebody's seen this, so it's a really weird equation. So maybe this is what Boris was saying, that there's some cyclicity going on because you always have delta and delta up, and there is indeed a cyclic structure, and this is the one that I so we do know that there's a nice cyclic structure. So if you rewrite this in these other graphs, so the one that I just had, this arc graph, then it's cyclic. And then if you do the boundary computation, then becomes this computation. So there is a nice thing. You have a cyclic structure, and you kill one of each of these arcs. And then you have to identify this with mu and delta op. And so you can actually graphically do that. But this is also the and this is then all these things become so that the tri bracket. So you have to check that if something is a double bracket, you have to check that some tri bracket vanishes, and this becomes very nice computation just in sort of taking diagonals in these things. So the graphical computations are really pretty. But if you like long expressions in algebra and Sweeter notation, you can also, actually Xingfeng loves those. So you can also write these things down. I only trust short. But this is so again, so this is the graphical version of this equation, which involves, all types of iterations of mu up and delta up. So does that look familiar, Boris, or? No, it's not.
Okay. Have to think. I don't know.
Right, I'll send this to you. But
thanks.
Yeah, as I said, I'm bad with typos, so there might be many typos.
Okay.
Okay, thanks.
Okay, thank you. So it looks like there are no other questions or comments. Let's thank Ralf for a very beautiful talk again. Yeah, thank you, Ralf. Yeah.